Chapter 7 is on exponential and logarithmic functions. We're going to first focus on exponential functions. So an exponential function is in the form of f of x, or y equals b to the x. So that b is the base and will be some constant number, whereas x is our variable. So the exponent now contains the variable. If our base is greater than 1, then we will have exponential growth. If our base, b, is between 0 and 1, we'll have decay. So notice it's not just positive or negative. It's if I'm greater than 1, it's growth, and if I'm a small fraction between 0 and 1, I will have decay. So exponentials are, like we said, growth or decay, and what happens is that all of a sudden something will grow super fast or it'll decay super fast instead of like a linear constant growth or decline. So some important characteristics of exponential functions. The domain here will be all real numbers, okay? And that's because if our exponent is x, we can put anything we want in there, right? We can put a positive, we can put a negative, we can put a 0. So your domain will always be from negative infinity to positive infinity. Now, exponentials will have horizontal asymptotes. Now, what is an asymptote? An asymptote is a line that a graph approaches but can never cross through. So for exponentials, we have a horizontal line. So it's an imaginary or dotted line that the graph approaches. Now, for our parent graph, which we will discuss, there's not one set parent graph. There's parent graphs per base. But for a parent graph, that horizontal asymptote will be at y equals 0. And I'll use HA to represent horizontal asymptote. Okay, so since it's a horizontal line, it's in the form of y equals. And again, it'll be at 0 for the parent graph. As my graph shifts up and down, that horizontal line is going to move up or down as well. And that's when we have a change in the equation. So I'll jot that down. Okay, so transform graphs will have a horizontal asymptote at the vertical shift. So if I say plus 2 and I go up 2, that horizontal asymptote will now be at y equals 2. If I go down 7, now my horizontal asymptote is at y equals negative 7. Therefore, to find the range, we're going to determine the horizontal asymptote. Okay, and so once I determine that horizontal asymptote, if it's up at 2, now I know my domain, my range will either start at 2 and go to positive infinity, or if the graph is flipped, it'll go from negative infinity to positive 2. Okay? All right, so let's look at some examples. I'm going to do 1 and 2 for you. So number 1 represents a parent function. So it's a parent function with the base of 2. So we could have a parent function with the base of 3, a parent function with the base of 1/4. So there's not one set parent function, but there is a parent function for the specific base. And notice there's no other transformations. Whereas if I look at number 2, I have that base of 2, but I have some transformations, okay? So 1 will be the parent function for example number 2. So we're going to graph it, then we're going to write the equation for the asymptote and state the domain and range. When we're graphing the parent function, you can simply just make a table of values. And when it's a parent function, since there's no transformations, I use the test points of -1, 0, 1, and 2. Okay? And so when I plug those in, 2 to the -1, recall, is really 1 over 2, so that'll be 1/2. 2 to the 0, anything to the 0 power is 1. 2 to the first is 2, and 2 squared is 4. So I'm going to plot those points. At -1, we're at 1/2. At 0, we're at 1. At 1, we're at 2. And at 2, we're at 4. So you can see that graph starts to increase, and then all of a sudden, it increases a lot faster and steeper. Now, I'm not just going to connect this in any old way. Remember, for my domain of a parent graph, that asymptote for the domain is going to be all real numbers, but for the range, that horizontal asymptote is going to be at 0. So with a different color, I'm going to represent the horizontal asymptote right here at my x-axis. So I know that this blue graph approaches that dotted line, but it never passes through. So therefore, that blue curve is going to look something like this. Okay? We'll get as small and as close to 0 as possible, but a negative exponent will never create a negative number. It just creates tiny little decimals. So I never fall below the x-axis. So what is the equation then for the asymptote? So that horizontal asymptote will have an equation of y equals 0. The domain for exponentials is all real numbers. And the range in this problem is, because it's exponential growth, because that base is 2, it'll be from 0 to infinity. And now notice 0 isn't included. I can never raise 2 to some power to give me 0. So 0 is not included. Okay? So now let's look at 2. For number 2, I'm going to use function 1. And so here's my trick. Even if I just gave you number 2 to do, I would focus first on graphing the parent function and then make my shifts from there. Otherwise, you could just make a table of values if you wanted to, but recall we have some shifts, so those test points are going to alter. So what I'm going to do is I'm going to take my parent graph and do the shifts. Recall here, all of my transformations are still the same as if it was an absolute value, a radical, a quadratic. So when I directly affect the x, that's going to be a horizontal shift. In this case, I'm subtracting, so remember, if I subtract, that means to go to the right 3. This -2 is my vertical shift, so that's telling me go down 2. So I'm going to take the points that I had that were blue, and I'm going to shift those the way the transformations say. So I'm going to use green. So if I take -1, 1/2, I'm going to go to the right 3, 1, 2, 3, and down 2. If I take 0, 1, I go to the right 3, 1, 2, 3, and down 2. If I take 1, 2, I go to the right 3, 1, 2, 3, and down 2. And if I take 2, 4, 1, 2, 3, and down 2. So the green represents my curve, but now we need to think about the asymptote so I don't just draw any old curve. What's happened, remember, to find that horizontal asymptote, our transform graphs will have a horizontal asymptote at the vertical shift. So since we went down 2, that means my horizontal asymptote will no longer be at y equals 0, but it will now be at -2. So I'll use that same orange to represent the horizontal asymptote at -2. And you can see we don't have any green points below that. So now when I connect my curve, we know not to go below. It'll go as close as possible, but it's never going to actually go below, and then we increase. So take a look at 1 and 2. Very similar looking, but since I moved to the right and down, it's just taken that blue graph and shifted it. So now if we do my domain, again, I can plug in any values. We can see we go to the left forever and technically to the right forever. And then my range this time is from our shift we went down to. So now the lowest it would go would be to -2, but not included. And it's still growth because of my base of 2, so it's going to go up to infinity. Okay, so now we're going to take a look at numbers 3 and 4. Notice this time for both of them, the base is a fraction, and it's a fraction that's between 0 and 1. So this time around, I'm going to have decay. Okay, so with decay, I'm going to do a basic one with you and then let you do the more challenging one. So for decay, still the same thing. I'm just going to make a table of values. And so for this problem, again, it's a parent graph, so I'm just going to test -1, 0, 1, and 2. When I plug a -1 in here, remember what's going to happen is that both of these, and I'll just do it out real quick for you, are going to get -1s. So now I need to flip-flop it so that 2 comes up top and 1 on the bottom. So I really get 2 when I plug in a -1. Now 1/2 to the 0, anything to the 0 power is 1. 1/2 to the first is 1/2. And 1/2 squared would be to square both of those, so I get 1/4. So let's plot those. At -1, I'm up at 2. At 0, I'm at 1. At 1, I'm at 1/2. And at 2, I'm at 1/4. Okay? Now, that asymptote, it's a parent graph. There's no other transformations. So that asymptote will be at my x-axis. So now you're going to just connect that curve. And what you can see here is this time around, whoopsies, don't want to make that look too high. This time around, the graph, when we read from left to right, it's falling. So it's decaying. Okay? So what I'd like you to do for finishing off 3 is write your equation for the horizontal asymptote, and then tell me your domain and tell me your range. For number 4, I'm going to have you do the whole thing out. Now notice, we're not going to use number 3 for number 4. This is not the parent graph. But my tip to you would be to do the parent graph and then to transform it. If that doesn't work for you, then go ahead and make a table of values. Okay? Give that one a try. There's lots of transformations. If you do well with this one, you're in really solid shape. Okay, now we're going to look at some models of exponential growth and decay, and we will see word problems throughout this whole chapter and spend time specifically just working on word problems. But let's do one of these examples together, and I'll have you do the second example on your own. So we have some formula that you want to have memorized for exponential growth and decay. And what it says is that a of t equals lowercase a times 1 plus or minus r to the t power. Now, notice here, this plus or minus is going to not always just be a plus or minus. You have to choose whether you think it should be a plus or a minus, which we will discuss, okay? But pretty straightforward. If it's going to be a growth function, we're going to add. If it's a decay function, we're going to subtract, okay? Little a represents the initial amount, r is our rate, t is our time, and then a of t is our new amount. So if we look at this scenario, it says the first U.S. census was conducted in 1790. At the time, the population was 3,929,214. Since then, the U.S. population has grown by approximately 2.03 annually. Approximate the population in 1820. So what we need to do is we're trying to approximate the population. So we don't know A of t, but we do know the initial amount. So that little a value will be 3,929,214. Now we know it's growing, so I'm going to have 1 plus. And that rate, don't just put 2.03. Remember, a rate, a percent, we move the decimal over 2 spots. So it'll be 1 plus 0.0203. And now our t value. What's our t value? It doesn't say 10 years. What we need to understand is that it was from 1790 to 1820. So how many years is that? That's 30 years. So I'll plug in a 30. So now you'll simply just use your calculator. So just to clean this up a little bit, what you need to make sure you're doing with your calculator is that you're following order of operations. So don't multiply the 3 million first. What we need to do is we need to raise 1.0203 to the 30th power. So hopefully you have a calculator for this. I'm not sure if your phone allows you to raise it to the 30th power, but if you have a calculator, the little caret symbol, so one that looks like this, if you use that, you can write to the 30th. So I would type in 1.0203 and then that value. So I'm going to put all that in at once, but I'm going to do 1.0203 to the 30th power. Gives me something like 1.827. I'm going to keep that in my calculator, though. I'm not going to round it because I want to be as exact as possible. Once I have that answer, I'm going to multiply by the 3,929,214. And when I do that, I get approximately, because now I'm going to round the end, 7,180,295. And we want to, since it's people, we don't want to put a partial person. So I rounded it to the nearest whole. Okay? So what I'd like you to try is the same thing, but approximate the population for 2020. Let's see how accurate this model is. See if it actually is a comparable answer to what the current population is today. Once you've done that one, go ahead and try the last example. Now, my hint for you for the last example is that a cup of tea contains 35 milligrams. The average teen can eliminate approximately 12.5% of the caffeine. Estimate the caffeine in a teenager's body after 3 hours. So if I'm eliminating it, we're going to decrease and start to decay. Okay?